Okay. So the test is next, Thursday. If you want to take it with a night class, you can take it on Wednesday night before. And what are the topics on the test? Yep, that's right. Harmonic motion and waves. So the stuff we're doing now and the stuff we've been doing for the last couple days is not on the test. And then we do have lab this week. So tomorrow. All right, and what have we been talking about? What were we talking about at the end of last time? You're like, I don't know what you were talking about, but we were talking about like how much we like the new layout of the cafeteria or whatever. But what was I talking about? Okay, yeah. So we were talking about the relationship between temperature and kinetic energy. Okay, so internal energy of a gas. Is equal to the translational kinetic energy of the gas plus the rotational kinetic energy. The internal energy of a gas, I'm going to give the name uppercase U. We're going to talk about that a lot. And so if we know the temperature of a gas, when do we know the total internal energy? When do we know the total U? What does it take? What are the properties of the gas that are required for us to go from knowing the temperature to knowing the total internal energy? Because knowing the internal energy is going to be an important thing. So I separated gases up into two types, like one specific type and then all the rest. What was it? Yes, that's right. So monatomic gases. Yep, that's exactly right. So monatomic gases. I always forget if you spell that monatomic. I think it's monatomic. Monatomic gases have very little rotational kinetic energy. And the temperature tells you the translational kinetic energy, which is basically all you have for monatomic gases. And so for monatomic gases, if you know the temperature, you know the internal energy. So the temperature gives the total U. Okay, so we're going to use that fact every time you're told that you have a monatomic gas. Okay, that's the only reason that I would tell you that a gas is monatomic. Well, there's one other reason that someone who's mean would tell you that you have a monatomic gas, and that's to try to trick you. But I'm not very mean in that way. So anytime in this class you're told you have a monatomic gas, you know that you're going to use that to calculate the total internal energy in some way. Okay. All right, so the next topic we're going to deal with is heat. And heat is one of those things where you have to sort of change your whole, so unfortunately there's like a colloquial, everyday language meaning of heat, and that's not what heat is in physics. So in everyday speech, heat means, I'll say, high temperature. Okay. And so you might think that the units of heat would be, degrees Kelvin or degrees Celsius or whatever. Actually, heat is a change in energy that's created because of due to a temperature difference between bodies. So the SI units for heat are heat is, a type of energy, and so the units are joules. So to wrap your head around this idea of like a change in energy due to something, in the first semester of physics, we talked about something like this. Can you think of so there was one quantity that we talked about that was a change in energy. It wasn't due to a difference in temperatures, but there was something that we dealt with that was a change in energy. So we talked about kinds of energy. We talked about kinetic and potential energy, but we also talked about one thing that was specifically a change in energy. And it was a change in energy due to the application of a force. Work, and it's related to the change in potential energy. But yeah, so work is like, think of heat as analogous to work. Work is a change in energy due to the application of a force. Heat is a change in energy due to a temperature difference. So energy flows from a high temperature body to a low temperature body via work. Okay. Work, heat, is a lot of times given in other units besides joules, so I need to give you a couple of conversions. So you'll often see heat in units of calories or kilocalories. And kilocalories, by the way, just to make this as confusing as possible, is what we call calories with a big C, like food calories. So kilocalories are actually what's on like food labels and stuff. 1 small calorie is the heat required to raise the temperature of 1 gram of water by 1 degree. So let me say, notice, so this is something that we're going to see all the time, and it's kind of evident in this definition of what a calorie is. Adding heat, or I should say, actually, let me say this quite differently. Increasing the internal energy of a body always increases the temperature. I guess there's one caveat I have to make: if there's no phase change, and we'll talk about phase changes a little later. But so there's this close relationship between internal energy and temperature. We know what that relationship is if we have monatomic gases. But if it's non-monatomic gases, you just have to know that there's this increasing relationship. Put in energy, the temperature goes up. 1 small calorie is equal to 4.186 joules, and 1 kilocalorie is equal to then 4186 joules. So that, I mean, I think the first time I saw that number, it's sort of a surprising amount of energy. You know, like a Tic Tac has 10 calories in it, so it has 41,000 joules of energy stored in it. That's a lot. So here's an example. If you consume 2,000 kilocalories a day, how many joules? So we're just going to do this conversion: 2,000 kilocalories, where 1 kilocalorie is 4186 joules, and you get a value of 8.372 times 10 to the 6th joules, so 8 million joules. Okay, so how high do you have to lift your body weight to use that much mechanical energy? So say if you have a mass of 70 kilograms, gravitational potential energy. Anyone remember what the formula is for gravitational potential energy? Is there a pi? Is there pi in it? Or E? Yeah, times G. Yep, so mg times height. Yep. So mass times 9.81 times the height. And so to create that much potential energy, 8.372 times 10 to the 6th is equal to 70 times 9.81 times h. So this is 68 point, I always forget this. Can someone just calculate all this stuff for me? I don't have any of this here. I just thought of doing this now. What if this whole notebook was just blank and I was just like making all this up as I went? What if it was all fake though? What if like halfway through the class, like a psychiatrist came in and was like, "There you are, you come with me now." Okay, so that's the height. Okay, so h is equal 12,191 meters. Okay, meters. Okay, so to burn a day's worth of calories, that's how much mechanical work has to be done. You have to climb, so 12,000, you have to go from sea level to the 50th highest mountain in the US. You know, from sea level, not from the base of the mountain. Okay, well, that's not really, I mean, this is just sort of meant to say that's a lot of energy, you know. You don't really have to climb Mount Everest to burn, and actually that's higher than the mountain part of Mount Everest, is it? No, a little lower. But it's in the right ballpark. So to go from base camp of Mount Everest to the top of Mount Everest is about, oh no, that would be feet. So this is way higher than climbing Mount Everest. Anyways, okay, I'm sort of fixating now. You don't have to climb Mount Everest to burn a day's worth of calories because your body doesn't convert metabolic energy into mechanical energy with very high efficiency, you know. But that's just intended to show how much energy there is in food calories, you know. Food calories are a lot of energy compared to the mechanical energy stuff that we calculate. And it's also, so I think this is sort of where I wanted to go with this. So a day's worth of food energy, that's thermal energy, okay? Your body's dealing with thermal energy. And the quantities of thermal energy that we deal with on a daily basis are really big compared to the mechanical energies that we deal with, and we'll see the electrical energies that we deal with when we talk about electricity. So thermal energy amounts in our daily experience are big compared to other forms of energy. We saw that when we talked about how much thermal energy there was just in the air, you know, a cubic meter of air. So big compared to mechanical energy. electrical energy also in our daily experience. And, you know, there are consequences of that. One of them is, you know, from experience, you know that if you plug two space heaters or a space heater and a hair dryer into the same circuit breaker, you know, the same circuit in your house, you short out the fuse. That's because you're using electrical energy to create thermal energy, and to create thermal energy that affects us in the way we're used to, it takes a lot of electricity. That's just sort of like an intuitive thing, but I think it's kind of interesting. We'll see when we talk about electricity that we're talking about even electricity that would have a big effect to us electrically is a surprising amount of energy compared to thermal energies that we wouldn't notice that much. Okay. So how much heat must be added to different materials to raise the temperature some chosen amount? Remember, I mentioned this last time. A process is when properties, let me say quantities, defining your chosen body, which could be a gas, are changed. I did one example last time where I talked about a process where a gas was inside a tin can. Do you remember the type of process I said that was? Or even if you don't remember the word, do you remember what I pointed out about it? Yeah, cost and volume, right. So if the volume is constant, it's called an isovolumetric process. And if this is true for an isovolumetric process, the change in internal energy is equal to the heat added. And I'm going to always denote the heat added as Q. I'm not sure why that's chosen, but when we start talking about thermodynamics, that won't be the case, but for now, in this section where we're talking about heat, the change in internal energy is just always equal to Q. The only way you can change energy is adding or removing energy by putting the thing next to something hotter or something cooler. Okay, so we're going to split materials, split gases. I guess we'll do more materials than gases. Split materials into two categories: monatomic gases and everything else. Okay, so monatomic gases. So what's the fact that's going to come into figuring out how to raise the temperature of a monatomic gas? How much heat is required? What? So there was something I said like 5 minutes ago, so that's probably why you don't remember it. So what's special about monatomic gases? Yeah, that's right. So what's special about monatomic gases is the total internal energy is equal to the total translational energy. The total translational kinetic energy. And therefore, the total internal energy you can think of as equal to the total number of molecules times 3/2 kT. So remember when we were in the temperature and kinetic theory section, we said that the kinetic energy of the average molecule, the translational kinetic energy of the average molecule is equal to 3/2 kT. Okay? So the total translational kinetic energy is equal to the number of molecules times 3/2 kT. And you can also write this as 3/2 times little n, the number of moles, times RT. Because the number of molecules times K is equal to the number of moles times R. That's a relationship that's always true between K and R. So that's why for monatomic gases, the total internal energy is equal to 3/2 nRT. Okay, so for monatomic gases, U is equal to 3/2 nKT, or 3/2 little n RT. This is true for monatomic gases only. And this big N is the number of molecules. Little n is the number of moles. So that means that a change in internal energy has to be equal to 3/2 nR delta T. So for an isovolumetric process, the heat added is equal to 3/2 nR delta T. And again, this is for monatomic gases only. Okay, so as long as the volume of the gas isn't changing, this is a way to calculate how much heat is added to the gas by measuring the temperature. This is one of those, so this is where you're starting to see why you have to be so careful about thinking about Q the right way. Q is a measure of energy, a change in energy. Temperature is, that's the way that you tend to think about heat in everyday life, but these are different things. This is a measure of an energy change. Okay, notice, so based on this equation, if this change in temperature is the change in temperature of our system, like of our chosen amount of gas, does positive Q mean energy is added to the gas or removed from the gas? "50-50 chance. If two of you answer, one of you will get it right." Added, yeah. So Q positive means energy is added to the gas. And the way you know that is, so if the temperature goes up, then delta T is positive. And that means that Q has to be positive. If the temperature goes down, delta T is negative, and then Q has to be negative. And to make the temperature go up, you have to add energy to the gas. Okay. Here's an example problem. How much heat must be added to 1 kilogram of helium gas to raise the temperature 1 degree Celsius? So the equation we're going to use, we want to use the fact that Q is equal to 3/2 NK delta T. Helium is a monatomic gas. And how do you know whether it's monatomic or not? It's not. It's a bummer. This room doesn't have a periodic table. Most of the rooms in this hall do. But the way you know this is the monatomic gases are the ones on the right side of the periodic table, the noble gases. So what we need is, we're given the change in temperature. We want to raise the temperature 1 degree Celsius, so the change in temperature is going to be +1. We have everything we need except the number of moles. So how are we going to figure out the number of moles? We're given the mass. What? Yeah, right, exactly. So yeah, we'll use the fact that 1 helium atom has a mass of 4. So every mole of helium has a mass of 4 times 10 to the minus third kilograms. And so 1 kilogram is equal to the number of moles times 4 times 10 to the minus third kilograms. So the number of moles is 250. And so now the heat you have to add to that gas is equal to 3/2 times the number of moles times 8.314 times +1, the increase in temperature, and you get a value of 3,117.75 joules. That was given in the problem. Raise the temperature 1 degree Celsius. So that's saying that the change in temperature is +1. If it would have said decrease the temperature 1 degree, then the change in temperature would be -1. Okay, so any questions about that calculation or any of that? That's everything you need to know about calculating the heat added to monatomic gases. So now we're going to do the same thing, but for everything besides monatomic gases. And so I'll be talking about non-monatomic gases, but also liquids and solids. We don't know as much about these things because we don't have any way of calculating the total internal energy. And so we have to make sort of an approximation. And this approximation says the change in internal energy is equal to the mass of the chosen object times a constant that you have to look up for that specific object and that specific phase of the object times the change in temperature. So this C is called the specific heat. Look up for your material and phase. And one way you can think of C is the energy required to raise the temperature's material that doesn't make any sense. To raise the temperature of 1 kilogram of material by 1 degree Celsius. Okay, so here's an example. So the volume of water in Lake Tahoe is 150.7 cubic kilometers. I just picked that one because when I was a kid, we used to go to Lake Tahoe every summer because my grandparents had a cabin, which just seemed like whatever, it was like going to the lake, but it was pretty cool. But I wasn't old enough to really appreciate it. But anyways, you would get there early in the summer, the lake would be 52 degrees or whatever, and at the end of the summer it'd be 63. And so how much energy does it take to raise the entire average temperature of the lake, let's say 1 degree Celsius? Okay, so I gave a volume of water. To use this equation, we need to get the mass. So how can we go from the volume to the mass? What's the quantity that'll get us there? We need to go from a volume to a mass, so density is the thing that'll help us. And the density of water is 1,000 kilograms per cubic meter. The specific heat of liquid water, which is different than the specific heat of ice and steam, is 4186 joules per kilogram degrees Celsius. 150.7 cubic kilometers is equal to 150.7 times 10 to the 9th cubic meters. The mass of the water is that volume, 150.7 times 10 to the 9th, times the density. And maybe I'll do this a little more carefully so you can see. Okay, so the volume is 150.7 times 10 to the 9th meters cubed. The density is 1,000 kilograms per cubic meter. So the cubic meters cancel and you come out with a mass of 150.7 times 10 to the 12th kilograms. Okay, so now the heat is equal to 150.7 times 10 to the 12th times the specific heat, 4186, times the change in temperature. We're trying to calculate a change of plus 1 degree Celsius, an increase of 1. And you get a value of 6.28 times 10 to the 17th joules. So that takes a lot of energy. And actually, I don't know, it's really deep, so maybe over by the shore where we're swimming, a temperature increase of 10 degrees doesn't mean that the lake goes up 1 degree. But anyways, it takes a lot of energy to raise the temperature of a big body like that. Where does that energy come from? You would think so, but most of it comes from people jumping into the water to go to the bathroom. So but some comes from the sun. I'm not sure. Some comes from each of those, and I don't know what the ratio is. Oh, that's true. Yeah, but it's probably always evaporating too. Okay, so now that we have a way to calculate the heat that it takes to raise the temperature of a body, we're going to talk about calorimetry. So, yeah, this? That's the mass. So I got that from taking the volume and multiplying it by the density. That's because this is 10 to the 9th times 1,000 just gives you the 12th. Oh, this should be 12th. Sorry. Okay, so like we've calculated the energy it takes, like without thinking about where that energy is coming from. We've calculated the energy that it takes that you have to add to an object to raise its temperature. So now we're going to talk about how if you have a bunch of objects in contact with each other, what happens when energy goes from the higher temperature thing to the lower temperature thing? How do the resulting temperatures and resulting energies work out? Okay, so let's say this has to do with the exchange of heat between multiple bodies in a system. And for any heat to be exchanged, these bodies have to have different temperatures. And the key to being able to come up with calorimetry equations is conservation of energy. If the system is isolated from its surroundings, and in practice that just means it's happening in an insulated container. Then any heat gained by one object in the system must be removed by other objects in the system. So that means that if you have a system of capital N isolated bodies, so this is just some number n, or let me say a system of n bodies isolated from its surroundings, then the heat added to body 1 plus the heat added to body 2 plus so on until you get all the way through all n bodies has to be equal to 0. So let's first, so we'll do this with and without phase change. It's simplest when there's no phase change, so let's start with that. So let's say that we have let's say we have 0.4 kilograms of water at a temperature of 20 degrees Celsius. And we drop in, let's see, well, I guess I'll just do this with water right now. I don't have a number for any metals right here, but so let's say we drop in 0.02 kilograms of water at 5 degrees Celsius. Okay. What's the final equilibrium temperature? And we're going to assume that this is insulated. So we can use this boxed equation. So what we want to do is we're going to take the heat added to the 0.4 kilograms of warmer water, add that to the heat added to the 0.02 kilograms of cooler water, and since we can express each one of these in terms of the temperature using the specific heat equation, we can calculate temperatures. So Q1 plus Q2 is equal to 0. We can rewrite that as the mass of the warm water times its specific heat times T final minus 20. That represents the change in temperature, plus 0.02 times 4186 times T final minus 5 is equal to 0. This is a single equation, so we can only solve for one variable. How did I know I could make these the same variable, these T finals? Like, can you think of an argument? Like, why is the T final of this going to be the T final of the other one? Yeah, because heat's going to keep being exchanged until they're the same temperature. Like, that's what heat does. It's a change in energy that comes about because of a difference in temperature, and energy is going to keep flowing from one to the other until they're the same temperature, until they reach T final. So in this case, we can divide both sides by 4186. We get 0.4 TF minus 8 plus 0.02 TF minus 0.1 is equal to 0. And so 0.42 TF is equal to 8.1. And what do you get for TF? Okay, 19.3 degrees Celsius.
Is the specific heat units in Kelvin, or is there any?
For specific heat, it is in, that's a good question. You can get it, you can figure it out from that equation. Joules per kilogram degrees Celsius. Why is this final temperature so much closer to the initial warm temperature than the initial cold temperature? Yeah, because there was a lot more of it. Yep. So remember that mass comes in there. I know somewhere in here I have other examples, but they're all mixed up. Maybe, so okay. Well, let me just say for now that you can do this, like these two materials don't have to be, it doesn't have to be water and water. You could do the same thing with water and like a ball of iron or something. You just have to know what the specific heat is for iron. Yep.
So, like with the variables left inside the equation, when it changed, if the material you're putting in changed, like the TF would still be the same.
That's right. So if it was iron, you'd still use that same TF there. I'll do an example of that next time class meets. I mean, we have a test coming up, but next time I have a chance to do it, I'll do an example with two different materials. There's no school on Tuesday. So let's talk about calorimetry with phase change. When a material reaches phase change, any phase change boundary heat added to the material goes into changing the phase not increasing the temperature. So if you graph the internal energy of water as it goes from ice to liquid to gas, it looks like this. Let's see. The graph I want to do is the temperature versus internal energy. So this is temperature, this is internal energy. And let's say that this temperature is in degrees Celsius. So you start out with ice at, and that's actually, let's say we start out with ice that's colder than 0 Celsius. This is 100, the boiling point of water. So start out here and add energy. And as you add energy, it has the effect of increasing the temperature, right? And what equation defines this line? An equation that I talked about today defines this line. Yep, so this goes with Q is equal to MC delta T for ice. Okay, this C is for ice. When it hits 0 degrees is the freezing melting point of water. So that's the phase change boundary. Then if you keep adding energy, for a while the temperature doesn't increase at all. Just little by little, that 0 degree ice is changing to 0 degree liquid. Okay? So after you've added some of that energy, you have mostly ice but it's, there's a little bit of liquid in there. Add more energy, you have more liquid and less ice until you finally get here and all of the ice is turned to liquid. Okay? At that point, it starts doing this again. And the slope is different than this one. But this part goes according to the equation MC C of the liquid delta T. And that goes on until it gets to the next phase change boundary. For water, that's at 100 degrees Celsius. And then the next bunch of energy you add just goes from converting 100 degree liquid into 100 degree steam. Eventually, it's all turned into steam. And if you keep adding energy, then the steam increases temperature according to MC C steam delta T. This heat is called the heat, not the feet, the heat of fusion. And this amount of energy, this heat, is called the heat of vaporization. And the heat of fusion and the heat of vaporization are called latent heats. And latent heats follow this formula. That the heat added is equal to the mass of the material times L. And this L is the latent heat for your specific material. And for the specific phase change that it's going through. For water, the heat of fusion, so the latent heat for going from solid to liquid is equal to I don't have that here either. Oh no, fusion I have. The heat of vaporization I'm going to have to give you later. Okay. So let's go back and look at this graph again and try to make sense out of this, because I think understanding this graph is kind of a key to being able to do these problems well. So first of all, why would they call that latent heat? I think this is sort of a helpful thing for understanding the idea here too. Why would they call that a latent heat as it's changing from ice to water and from liquid to gas? Can you think of an explanation for that? I think the best way to think about it is if you're trying to judge a material's energy by its temperature, then when they're in these regions, there's an energy being added that doesn't show up in the temperature, okay? It's gaining energy, and it's storing up that energy, but it's storing it up in a phase change rather than in a temperature, you know? So, so like when you go from, let's say that you have a material right here. What's the state of the material here on this graph? What would this point be? So it's ice over here heating up until it's ice at 0 degrees. And now you're adding this extra energy, and here it's liquid at 0 degrees. Okay? And does that make sense? Okay. And when you have this liquid at 0 degrees, this liquid has a latent heat. It has this energy inside it due to its structure that can be removed from it without changing the temperature. Okay? So you could use, and in air conditioning systems and heating systems, this is done. You can use this energy that's in this liquid at 0 degrees, turn this into ice, and you still haven't changed the temperature of the gas at all. You haven't changed the temperature of the material at all. Like in that sense, it's latent. It's waiting there, not being used to change the temperature, but that energy is available for use, for transfer to other things. Okay, what's the state of the material right here? That's a liquid at 100 degrees Celsius. What's the state of the material right here? It's half and half. It's at 100 degrees Celsius, but it's half of it is steam and half of it is liquid. And this graph holds whether you're adding or removing energy from a material. So if you started with a material in this state, so this is called a superheated vapor. Then if you removed energy, its temperature would decrease until it became all steam at 100 degrees Celsius. And then the next bunch that you removed would only go to changing from steam back to water, to liquid. If you kept removing energy, then the temperature would go down until you got to the freezing point. Then removing more energy would change the liquid into ice at 0 degrees. And then removing more energy would decrease the temperature again. Any questions about any of that? Okay, I'll go into some example problems of how to use this equation in calorimetry next time. So yeah, Tuesday there's no school. It's Success Day. Does everyone know about what Success Day is? There's just like little lectures and stuff going on, just sort of for your personal edification all day. And so, you know, see if there's anything that looks interesting to you. But there aren't any classes. And then Thursday is the exam. And then the next Tuesday, I'll get back into this stuff and talk about how to use this in calorimetry. Okay. Yeah.
It is 2260 kilojoules per kilogram.
Okay, thanks. That sounds familiar.
I wanted to shout that out. I have my phone on Wi-Fi at the manual and stuff.
Oh, okay,
I'm
thanks.
Watching your,
Okay.
I'm watching your equation chart. I did have a question. Or would you rather I do it